All right, welcome to The Explainer. Today we've got a really cool puzzle for you. It's all about finding hidden connections between a group of students, and we're going to look at the incredibly powerful tool you can use to uncover them. It's a great story about patterns, networks, and a really clever way to search. So let's set the scene. Imagine you have this big group of students, and they each have scores in three subjects: maths, physics, and chemistry. Now, here's the rule. One student can mentor another student in a subject, but only if their score is between 10 and 20 marks higher. Simple enough, right? But here's the twist. We're not just looking for a one-way street. A helps B. We are on the hunt for a perfect closed loop, a three-step study circle. So think of it like this. Student A mentors student B in maths, then student B mentors student C in physics, and, this is the crucial part, student C mentors student A right back in chemistry. A perfect circle. So that's the big puzzle, isn't it? With a huge group of students and all their scores, how on earth would you even begin to search for these complex hidden loops? How do you find these little teams? Well, you've got two options, and option one, the painful way, is, well, it's exactly what it sounds like. You could try to brute force it. You'd have to check every single student against every other student for every possible mentorship in every subject. It's just agonizingly slow. Yeah, painful is the right word. You can just feel how long that would take. There has to be a smarter way to do this. And lucky for us, there is. It's a two-step process. First, you prepare the data in a clever way. And second, you use a really powerful search strategy. And that smarter way starts with something super simple, but really powerful: just getting our data organized. Instead of a random mess of scores, we're going to arrange them intelligently. See, just by sorting the students in each subject from the highest score down to the lowest, we've created this huge shortcut. All of a sudden, if you want to know who student 8 can mentor in maths, you don't have to check everybody. You just look right down the sorted list. It is so much more efficient. Okay, so our data is prepped and ready to go. Now we need the search strategy itself. And this is where this brilliant idea comes into play: an algorithm called depth-first search, or DFS for short. Now look, don't let the name algorithm intimidate you. It's not about complicated code. The best way to think about it, it's just a simple but powerful set of rules for solving a maze without getting lost. It's a strategy. I mean, the name says it all, right? Depth first. It picks a path and it just goes. It dives as deep as it possibly can down one single route. And only when it hits a dead end or finds what it's looking for, then it backs up to the last choice it made and tries the next path. It's systematic, and it never misses a spot. Okay, that's the theory. But let's actually see this thing in action. This is the cool part. We're going to watch DFS use our sorted lists to hunt for a real mentorship cycle. And we'll kick things off with student 8. So here we go. We're starting our search with student 8, who has a pretty high score in maths, making them a perfect starting point. All right, first step. Using that sorted list we made, DFS instantly finds a path. Student 8 can mentor student 1 in maths. So the algorithm follows that path, and importantly, it makes a little note. Okay, we've used maths. Now, from student 1, we don't stop, we go deeper. DFS looks for who student 1 can mentor in one of the other subjects, and bam, it finds one. Student 1 can mentor student 12 in chemistry. Our chain is now 2 links long. And here it comes, the magic moment. From student 12, the algorithm checks the last subject we haven't used yet: physics. And who can student 12 mentor? You guessed it, student 8. We are right back where we started. And there it is, cycle found. The algorithm just dove deep into this web of possibilities and found its way right back home. It successfully uncovered one of those hidden mentorship circles. This is that exact aha moment that the source material talks about. That feeling of, wow, that is nice. It's the payoff for doing things the smart way. We just found our first perfect study group, students 8, 1, and 12. So finding one cycle is awesome. But the really interesting question here is, why does this method work so well? What's the secret sauce? Well, for starters, DFS is totally systematic. It checks every possible path, so you're guaranteed to find any cycle that exists. But the real genius, the part that's just so cool, is that the network of connections, the graph, doesn't have to exist beforehand. The algorithm builds the map as it goes. It finds the connections on the fly, and because our lists are sorted, that discovery process is lightning fast. Yeah, this quote just nails it. The map of all the connections, it isn't there when you start. The algorithm is creating the graph as it explores. It's pure discovery. And the search doesn't just stop after finding one cycle. Oh no. Once it finds one, it just backtracks and keeps on searching, systematically sniffing out every other hidden study group in the data. Like, it finds a two-person cycle and even another possible group for our original student, number 8. And that really brings us to the big idea here. This was never just about students and test scores. It's a universal strategy. When you combine intelligent data preparation with a systematic search, you can untangle incredibly complex problems and find patterns that were hiding in plain sight the whole time. So, I'll leave you with this question to think about. We used this method to find study circles, but what else could you find with it? Think about it, from hidden communities on social networks to the most efficient routes in a supply chain, or maybe even spotting patterns in financial markets. What other invisible networks are out there, just waiting for a systematic search to bring them into the lights?